radio waves tend to be on the left side of this spectrum. They are long wavelength. As you move towards the middle, we start to get to intermediate wavelengths, and somewhere in here, you'll see sort of in the middle of the plot, there's this rather thin sliver which happens to correspond to wavelengths associated with what we call visible light. Okay? Let's keep going, and then I'm going to come back to give you a sense of how special visible light is for us. If we keep going to shorter wavelengths, we're getting into things like UV, ultraviolet, we're getting into what are generically called X-rays, and then we come to call them in the shortest wavelengths gamma rays. Okay? And again, you can sort of see senses of scale associated with this. So the visible light spectrum, why is it special for us? It's special for us because we've adapted such that our eyes are sensitive to this part of the electromagnetic spectrum. So, visible part of the spectrum runs from wavelengths between about 400 nanometers, so 400 times 10 to the minus 9 meters, up to about 700 nanometers. So just from 4 to 700 nanometers over this entire possible electromagnetic spectrum. It's a tiny, tiny, tiny part of the spectrum that our eyes are sensitive to. And so in this sense, it's kind of amazing that we've evolved this way. There's no accident that this is so. And there are many ways in which that's manifest, but for example, the fact that we live in the neighborhood of a star that is active, it's producing energy by nuclear fusion, and it happens to be that the electromagnetic radiation that it spits out into the universe around it peaks in its spectrum in this part of the wavelength region, so a few hundred nanometers. So of course that's no accident that our eyes have evolved to be sensitive in that range. But I want you to take away from this the remarkable thing that we experience via light, an incredibly small part of this rich electromagnetic spectrum. And if we were sensitive to other parts of the spectrum, we would see all sorts of remarkably different things. Okay? So sadly, I don't have time to talk much about that. I could talk about it at great length. Let me show you now a couple of demonstrations about visible light. First off, something I'm sure you've all seen before, which is trying in one of two ways. The first one, the most simple, to convince you that what we see as, let me say, white light is actually a composite or superposition of the various wavelengths across that 400 to 700 nanometer range. So there's a white incandescent light. So incandescent light source, which to good approximation our eyes perceive as being kind of white, possibly slightly yellowish. And what's happening here is I'm simply shining that light through an appropriately shaped chunk of some transparent material, in this case glass. And for reasons we're not going to have time to talk about, the light as it passes through it gets bent as it travels through the light. And it turns out the angular deflection depends on the wavelength of the light. And so this gives rise, of course, to the phenomenon of rainbows. And so you'll see in various places around the room now rainbows that are showing the white light being split up into different wavelengths that our eyes perceive as different colors. Okay? So red through orange, yellow, green, blue, indigo, violet. And again, just remind you that this is a tiny, tiny part of the electromagnetic spectrum. So that's one thing to show you. And then the second thing is kind of a little bit of fun. Show you something similar, but in a different context. So this is where you get to play with fun toys.
I want him to throw them at. Don't pass it. Do you have a handful of this?
Okay. Grab a pair of glasses. Just grab one of these and pass them on. We're going to get some more. These guys don't have enough. Okay, I have to warn you that they are not sunglasses. Do not look at the sun through these. They will not protect your eyes from getting damaged. Okay, if you guys can send these back, if one we give them the back, it's always
And you get sunglasses. You get
walk up
sunglasses.
and pass them.
You, sorry.
Okay. So,
I get my extra pair of glasses.
hold on.
Yeah.
There are 3
All right.
screens.
So, what you have here are glasses that have, instead of just regular pieces of plastic or glass where the lenses should be, they are thin sheets of plastic which actually turn out to have lots and lots of very small parallel lines etched in them. Again, if you go on and do more physics, particularly wave physics and optics, you'll learn more about it. But they are exhibiting a phenomenon called diffraction, which has to do with interference of nearby waves, in this case, of course, waves of light, that travel slightly different distances on the way to your eye, and in doing so, they either add up to give more light, or they cancel each other out to give less light. That's an interference phenomenon. Again, those of you who do third semester physics will do a lot of this. So all of this to say that it gives us an alternate means of showing how light can be bent by varying amounts depending on its wavelength. Okay? So I've got a couple of light sources here to show you, if I can figure out how to turn them on. Let's see what's going on here. Okay, this is slowly coming alive. So, what do you see?
Three
Okay,
lines.
aside from pretty colors, let's hear a little more.
3 lines. Many lines.
Bands of colors, okay.
Wow.
And they are, at least with my glasses, they're off to the sides.
Yeah, they're off to the sides.
Okay. But to some extent, well, okay, you see certain bright lines, but you see to a large extent most of a rainbow, okay?
Yeah.
Now, what I'm going to do is show you a couple of other light sources, and I want you just to look at these and compare and contrast with what you see on this one. So let's try this.
I have like that here, and then there's a
So there's a real rainbow, okay? More or less a continuous rainbow. But what you'll notice are, in fact, there are parts of the rainbow that are missing. There are dark lines, okay? So we're going to think about that. This is more or less an incandescent light bulb, but it's enclosed in a glass casing that has a particular coating on it. So that's an incandescent light bulb with a glass casing that's coated with something. This is a light bulb that is filled with a certain type of gas. In a moment, you might even tell me what it is. So now here you're seeing a few distinct colored lines separated by, roughly speaking, areas of darkness. Let's see what else we've got over here. So maybe I'll leave these on.
This isn't fair, it's just too cool.
Put it in the hole.
Whoa. Wow.
Okay, so let me see what you're looking at.
This is trippy.
Okay, it's kind of gotten a bit complicated. Alright. So, I'm going to get rid of this one. I'm going to get rid of this one. And maybe just leave these two. Okay. So, what do you see? If I was to ask you to summarize these various observations with your glasses, what do you see when you're looking at these light bulbs?
The separation of the light into distinct like bands
Okay.
that rises the light that we see.
Yep. Okay, so since we know that if I've got white light and I bend it through a particular device like a glass prism or one of these sets of diffraction glasses, what we know is that the angle at which light is deflected depends on the frequency or wavelength of the light. So in these cases where you see that the light only appears with certain colors at certain, let's say, angles or certain positions, what's that telling you about the light source, the light sources? So here we've got, in the case that I showed you, the incandescent light bulb, or this light bulb. We saw the whole rainbow. But for these ones that you're looking at, we don't see the whole rainbow. We only see very small parts of it with certain well-defined lines and certain colors. What does that tell you about the light source?
It's probably not like just regular air.
Okay, let's keep going. How?
Is there some interference going on?
Is it what?
Is there some interference going on with like the air?
I'm not going to call it interference, nope. Let's talk about the source of the light. Well, even, go ahead, Michael.
It's only emitting certain wavelengths
It's
of light.
only emitting certain wavelengths, right? Okay, so this is going to be one of the first sorts of hints that you may experience, that these sources of light have something special about them. It means that they can only generate light with very specific wavelengths and frequencies. And what you're actually seeing here are lights that are filled with different chemical elements. I think this is argon. The one that I have here, I've turned off, is neon. Somewhere in here is helium. And so each of them have characteristic, what we might call spectral fingerprints. So they each have certain particular wavelengths or frequencies of light that they are able to emit. What might that be telling us?
Quantum phenomena
Okay.
that possibly wavelengths can only be emitted in certain distinct chunks of
Yep.
energy.
Okay. So that's exactly what you're seeing here. The fact that certain elements, again, a lot of these are noble gases, helium, neon, argon. It turns out that whatever light they're emitting only comes with certain frequencies or wavelengths, and very small number of them. So this is one of the earliest hints that you would see in the development of physics of what are called quantum effects. Okay? And of course, beyond 2 semesters of intro physics, we typically will start looking at quantum phenomena next, if you're going on to do more physics. So what it's telling us is that at the microscopic level, at the atomic level, there's something intrinsically quantized, which means it comes in discrete chunks, about almost every type of physical process. And you know what's underpinning this, either from chemistry or physics in your high school, most likely. It's a reflection of the fact that electrons in atoms can only exist in well-defined discrete energy states. Okay? So these spectral fingerprints, where you're seeing very clear lines at certain frequencies, are actually representations of possible electron jumps in the atoms as they jump between a few allowed energy states. And it turns out that the frequency and wavelengths of light are associated with their energy and momenta respectively. Okay? So this is a first sort of glimpse into a quantum world with light. And it's also not a bad time for me to say something else about light, which is kind of interesting. Having just in the past 48 hours learned that light is a form of electromagnetic radiation, electromagnetic wave, you might be inclined to think that light is a wave phenomenon. And in many respects it is. But it turns out that light itself, depending on how we're observing it, can behave not as a wave, but in terms of something which is entirely different, namely something that looks like a particle. Okay, and again, a very remarkable thing in the quantum world of small-scale physics. Things basically behave simultaneously as though they have wave characteristics and particle characteristics. Okay, and so we end up looking at the particle's nature of light in many important respects, and we end up calling these particles of light photons.
Yes.
And in many respects, a lot of phenomena in quantum mechanics have to do with light being treated as a particle rather than a wave. All right. So, with all of that said, do I really want to talk about energy and momentum transfer in electromagnetic waves? I'm actually not going to do anything quantitative on the chalkboard. I'm just going to have you guys read a couple of pages of notes and a couple of sections in chapter 32 of the textbook. I'm just going to talk qualitatively. Let me bring you back to this. This tells us that in vacuum, there's a unique prediction for the speed in which electromagnetic waves, including light, travels. Notice what's here, epsilon 0 and mu 0, permittivity and permeability of free space. We spend a little bit of time talking about materials that have dielectrics, that have permittivities, that are not those of vacuum, but in fact they're the permittivity of the material. And though we barely touched on this at all, the same thing is true of materials and magnets. There are materials that have their own material-specific magnetic permeability, mu. Okay? Now, we barely talked about this for magnetism with mu, but we did talk about this for electrostatics and epsilon 0. You know that in materials, epsilon 0 goes to a value epsilon, which is greater than this value. Okay? So this is bigger than this, always. This is bigger than this, always. What does that tell you about the speed of travel of electromagnetic waves in materials? Yes. So if light or any other electromagnetic wave travels into materials, it travels more slowly. Speed of travel is actually less than the speed of light in vacuum. Okay? And so, this may sound slightly strange, I don't know, but as light is passing, for example, through this chunk of glass, instead of traveling at 3 times 10 to the 8 meters per second here, it's traveling about 30 or 40% more slowly as it travels into this chunk of glass, comes out the other end, and it's going back at 3 times 10 to the 8 meters per second. And this change of the light travel speed in materials also has something to do with the refraction effect that you saw and the variable degree of bending of the different colors of light as it goes through the material. So this is interesting. I want you to keep in mind that light can travel faster than C, and it does when it goes through materials. And in fact, there are examples, not many of which, probably none of which you've actually witnessed yourself, but there are examples around us where we can see phenomena associated with objects, particles typically, traveling faster than the speed of light in materials, and when they do so, they produce shock waves. Okay? So you know that when you go faster than the speed of sound, you've got something moving faster than the speed of sound, it produces a shock wave, a sonic boom. There's a similar effect with light. If things are moving faster than the speed of light in the material, they produce an electromagnetic shock wave. And there are examples of that around us. The one that I'm thinking of most immediately, if any of you have ever seen images, photographs of nuclear fuel storage tanks where nuclear fuel is stored underwater, this is often done for various reasons, you might actually have seen instances where there appears to be a blue glow associated with that. That's an example of an electromagnetic shock wave of particles moving faster than the speed of light in water. Okay.
Wait, I thought the speed of light was like the cosmic speed limit and all that.
Speed of light in vacuum is a cosmic speed limit.
Okay.
But now we're talking about electromagnetic waves in matter.
Oh, okay.
So yes, the speed of light in vacuum is a cosmic speed limit. So we've got a bunch of questions.
When you say that, like, things travel faster than the
Yes.
speed of light?
In the material, yeah.
Is it light traveling faster? Or is
No,
it-
it's other, let me say, fundamental particles, like an electron, for example. It's perfectly possible to have an electron move faster than the speed of light in some material. Of course, it's not possible for an electron to move faster than the speed of light in vacuum. There are a bunch of questions. Kate?
So like, it's possible for particles to move faster than light would in that material, but it's still moving slower than light can in that.
Correct.
Okay.
Yeah.
Wait, so is this totally unrelated to the phenomenon of the way we have space? Then it's like, you know how the universe is expanding faster than the speed of light, but it's actually like the space that's it's
So
just like
I'm not
it's
sure.
totally
I'm
different.
not sure I want to say the universe is expanding faster than the speed of light. Quite how the universe is expanding is remarkably subtle and difficult to describe, but it is true that there are parts of the universe that are moving away from each other at faster than the speed of light.
Is that the same phenomenon as light moving through matter faster than the speed of light in
No,
vacuum? Or
not at all. Totally unrelated. Yes.
If light can travel like slowly through materials, how slow can you make it?
Okay. Great question. How slow can I make light move? So in a conventional way, by tuning these parameters, probably not much more than, well, depends how you measure it. But let me say it the simplest way, not much more than, I don't know, a factor of 10, maybe 100, something like that. But depending on how you measure the speed of light, you can slow it down to basically sort of human scale day-to-day life speeds. And I remember maybe 7 or 8 years ago, a nice result from a researcher at Harvard, I've forgotten her name, I think she's Danish, but she was working on experiments that effectively showed she could slow down light to basically walking speed in the lab. And it depends how you measure it, but it's basically a measure of how quickly information associated with the wave travels a certain distance. It showed she was able to make it go at basically walking speed.
If these particles moving faster than the speed of light through a material, you assume that light is going to move faster than those particles in that material?
No. So light is going to go whatever the speed is, again, the simplest way defined by this, it is going at that speed depending on the material. No ifs, ands, or buts. It's going at that speed.
With E naught and mu
With
naught?
epsilon and mu that are material specific. So light is going to travel at that speed and only at that speed in the material, where epsilon and mu are different than the vacuum values. So that defines for you the light travel speed in that material for light. That's not to say that other things can't move at other speeds, and they can, both slower and faster. But the light itself has to go at a certain speed depending on the material itself. Okay, so we're very much in sort of general question mode here, which is great. Let's just keep going. I'm going to forget about all this stuff. Ariel?
When you say that something travels faster than light in a material, it still can't go faster than C, right?
Correct. Right. Yeah. I mean, because people question the fundamentals of science and physics all the time, you might ask yourself, well, are there really things that can go faster than light? And people trying to do experiments to see if there are, and so on and so forth. But for now, we're convinced that nothing moves faster than C. Noah.
So like, what is the like fundamental nature of like a vacuum for which the maximum speed of light travels? Like, do quantum fluctuations and all that junk like play into the speed of light? And like, if there's no, like, because isn't there like stuff that's happening on like quantum scale that affects
Yep.
it?
You're right, the vacuum, what is the vacuum? It's space when we've taken everything we can out of it. Okay, so it's easy to take matter out of space, more or less. In some sense, we can even sort of take what we think of as energy out of space, and you know from special relativity a little bit that energy and matter are just different manifestations of the same thing. So in some sense, that's doing the same thing, but in practice, it's harder to take energy out of space. But if you take everything that you can out of space, that's what we define as being a vacuum, but it isn't empty. You're right. And the reason it isn't empty has to do with quantum effects, and in particular has to do with what's called the uncertainty principle. which indicates that it's possible to have essentially short-lived, spontaneous outbursts of energy in empty space, so long as they only live for a very short amount of time, where that time window is determined by this thing called the uncertainty principle. So the uncertainty principle in this context gives us an upper limit on how much energy we can temporarily borrow or produce from nothing before we have to put it back. And so the analogy that's often used here, no idea why, is it's kind of like being able to steal money out of a bank and use it for a while so long as you put it back before nobody looks, okay? So it's the same idea, where you can steal energy from the vacuum for a short amount of time as long as you put it back before you can uncertainty principle. So that has enormous impacts. To be honest, I don't know that it has any relevance to the speed of light, but it does have tremendous relevance for our universe as a whole and how it seems to be evolving over time. In particular, if you associate that phenomenon with the expansion of the universe, the fact that our universe is growing increasingly quickly, if you believe that those two things are related, and probably they are, and you try and calculate what the effect is, you get an answer which is famously wrong by a factor of 10 to the power 500. Okay? So the observed so-called energy density of the vacuum is smaller by 10 to the power of 500 than you would expect from the calculations from quantum mechanics. So this is a big problem. 10 to the power of 500, you will get some points off on your homework. Screwed up at that. Okay, other questions?
Try again.
I guess we're going to wrap up here. I'm not going to tell you anything about energy and momentum transfer. Other questions about electromagnetism, about the universe?
What's your favorite color?
Go on, you put me on the spot. Blue. Okay, how's that? All right. Okay, other questions about fundamental physics or less fundamental? Yeah.
What shade of blue?
That one I'm not answering. What other questions you guys have?
Do you feel like there could be one?
I'm going to regret this, I can tell.
No, listen. Do you feel like there could just be one equation that describes all of physics?
Okay. So, those of you going on to do more physics, and even if you're not, I mean, think about these things, read about them, they're interesting questions. There's been enormous progress over the past few centuries in seeing similarities between different, very different phenomena in the world around us. Electromagnetism is really the first example you guys have experienced at first hand. So electricity and magnetism at face value look completely different, and yet now you've seen that they're just aspects of the same thing. I didn't get a chance to talk about relativity in this context. For those of you who are interested, I'm going to post about 30 pages of reading on that coursework. You need to read it. But we've had enormous success in unifying different aspects of the physical universe around us. And given that success, people are inclined to think that the idea of a more high-level global unification of all different phenomena, all different fundamental forces, is possible. And of course, people have been working on it. So aside from the unifications, well, what else do you know about unifications? This one may not sound like a big deal, but it was back in the day, thanks to Newton, the unification of terrestrial and extraterrestrial gravitation. In fact, you can describe near-Earth gravitational phenomena and those on the scale of the universe itself by a single theory, which is kind of surprising. So that's the first unification. Electromagnetism would be the second. The third, more recent, really in the 1960s, I would say, was unification of electromagnetism with what's known called the weak nuclear force. And that seems to have been successful. So right now, I would say we are at the point where we have, this a little bit depends on how you count and at what energy scale you're living, but right now I'd say we have three distinct forces.